Three engineers in Mountain View made a decision in 2018 that may end up being the most valuable hardware decision in AI history. They decided to wire 10,000 chips together with light, not copper. Today, that single decision is what lets Google train models that no one else can train at the same scale. Every other hyperscaler is now copying it. Microsoft, Meta, AWS, ByteDance, they all want the same fabric. The actual semiconductor industry view of the AI race in 2026 is simple. The chip war is not won by chips, it is won by light. And the two American companies that ship the optical hardware nobody else can match are about to become some of the most strategic suppliers in the industry. To understand why this matters, you have to understand the wall that copper hits. Every interconnect on a chip, every wire from one transistor to another, every cable from one rack to another, has a fundamental trade-off. The faster you push bits down a wire, the harder the bits are to recover at the other end. Beyond a certain bandwidth, you cannot recover them at all. The signal melts into noise. NVLink, link, NVS switch, PCIe. Every electrical interconnect lives inside this wall. Engineers have squeezed copper for 30 years through better signal processing, error correction, equalization. Each generation buys 2 to 3 more years. None of them break the wall. Light does not have this wall. A photon at the wavelength used in data centers can travel hundreds of meters with negligible loss. The bandwidth distance product of a single optical fiber is millions of times higher than the best copper trace. The entire telecom industry has lived inside this fact for decades. AI has just discovered it. Take a concrete example. The interconnect inside an NVIDIA Blackwell rack runs at 1.8 terabytes per second per chip. The cable length is roughly 50 centimeters. Past that, the signal degrades. Past 2 meters of copper, you are forced into expensive retimers, and the bandwidth drops by half. Past 5 meters, copper is dead. You must convert to optical. This is why a single Blackwell rack can connect 576 chips, but to connect 2 racks together, you have to go optical. And the bandwidth between racks is roughly 1/10 the bandwidth inside a rack. Networking topology, people call this an asymmetric fabric. Training algorithms hate it. The all-reduce operation that synchronizes weights across the cluster runs at the speed of the slowest link. If the cross-rack link is 1/10 the speed of the in-rack link, your training is bottlenecked by the cross-rack link. Now multiply that across a 9,000 chip cluster, across hundreds of racks. The aggregate cost of asymmetric bandwidth is enormous, both in dollars and in training time. Google's answer was to skip the in-rack copper entirely. Every chip in a TPU pod talks to its neighbor through optical fiber, and the central switch that routes between them is an optical circuit switch. The fabric is symmetric. There is no copper wall to hit, no asymmetry between racks, no expensive retimers. Bandwidth is the same between any 2 chips in the pod, whether they are in the same rack or 50 racks apart. The OCS itself is a mechanical device. Inside the box are arrays of microscopic mirrors. Each mirror is roughly the size of a grain of sand, sitting on a silicon substrate, suspended by tiny beams that let it tilt. There are hundreds of these mirrors per OCS arranged in 2 banks. Light from a chip enters the box, hits a mirror, reflects to a second mirror, and exits to another chip. By tilting the mirrors, the OCS routes any input port to any output port. It is, mechanically, a 19th century telegraph rotary switch, except built at the scale of human hair, controlled in microseconds, switching wavelength bands of light. The trick is that the OCS does not look at the data. It does not parse packets. It does not buffer anything. It just reflects light from input to output. This means the latency through the switch is the speed of light over a few centimeters, about 100 picoseconds. And the bandwidth is whatever the optical link can carry. Compare that to an electrical packet switch like a tomahawk. Bandwidth is bounded by the silicon, latency is hundreds of nanoseconds, and every packet has to be parsed and forwarded. The OCS strips all of that out. The reconfiguration time matters too. If your workload changes, you can retilt the mirrors and rewire the topology in tens of milliseconds. Google uses this to dynamically reshape the fabric for different jobs. Training one model uses a torus. Training another uses a tree. Serving inference uses a star. Same hardware, different routing. NVIDIA does not have this. Cisco does not sell this. Broadcom does not sell this. Google built it themselves with optical components from companies you have probably never heard of. OCS is the first wave. The next wave is co-packaged optics, CPO. The idea is simple. Take the optical components that today live in a separate transceiver module 2 centimeters from the chip and integrate them onto the same package as the chip itself. The light source, the modulator, the photodetector, all bonded directly onto the silicon. Why does this matter? Power and density. Today, every transceiver consumes roughly 25 watts to push light into the fiber. In a 9,000 chip pod, transceivers alone consume hundreds of kilowatts. CPO can cut that by half because the electrical signal from chip to optical engine is millimeters instead of centimeters. The bandwidth density also explodes. Instead of 800 gigabits per second per pluggable module, you can get terabits per second per millimeter of chip edge. NVIDIA announced CPO support for the next generation Blackwell platform. Google has been shipping CPO-style integration in TPU since V5. Microsoft is building it for Maya. The supply chain for CPO is still forming. The light sources still come from a small set of vendors. The integration steps still happen at OSAT facilities outside the chip foundry. But the trend is clear. By 2028, every hyperscale AI accelerator will have optics on the package. The companies that supply those optical components are about to see demand grow by an order of magnitude. The question is whether they have the supply to meet it. Two American companies sit at the center of the supply chain. Coherent, the result of a 2022 merger between T6 and the original Coherent Inc., controls the NP wafer fab, the laser diode production, and the high-power semiconductor optical amplifier business. They are vertically integrated from substrate to module. They sell to every hyperscaler and every transceiver vendor. Their optical revenue runs at well over $5 billion annualized and is growing faster than the broader semiconductor market. Lumentum, descended from JDS Uniphase via a series of spin-offs, owns the MEMS optical switch IP that Google's OCS is built around. Lumentum also makes the tunable laser arrays used in coherent optical transceivers, the workhorse of long-distance data center interconnect. Their datacom segment is now their fastest-growing line. Behind these two are smaller specialists. AOI ships VC cell arrays. POET makes silicon photonic interposers. NeoPhotonics, before being acquired by Lumentum, made coherent receivers. The supply chain has consolidated to a small number of players, and demand from AI is now growing 4 to 5 times faster than supply can ramp. This creates the same dynamic the HBM cartel created in 2023. When one customer takes a multi-year capacity deal, every other customer is locked out. Microsoft has reportedly signed an NP wafer offtake with Coherent that consumes 2/3 of their next-generation capacity. The rest of the industry is fighting for what is left. The optical supply chain is the next HBM. The names are different, but the dynamic is identical. Small number of suppliers, exponential demand, capacity contracts that decide who can train at scale. The verdict: 2 layers, 2 winners, and 1 observation that ties the series together. First, Coherent. They own the NP wafer supply, the laser diode production, and the SOA business. Without them, no transceiver ships at scale. The NP capacity moat is at least 3 years deep. Coherent's optical systems revenue is growing faster than NVIDIA's, with margins that are defensible because the underlying compound semiconductor process has no second source. Second, Lumentum. They own the MEMS technology that powers Google's OCS and the tunable laser arrays inside coherent transceivers. Their datacom growth is structural, not cyclical. Every TPU pod Google builds, every Ironwood cluster they deploy, every CPO module that ships from 2028 forward is partial revenue for Lumentum. The series observation is this: every episode of AI Supply Chain has named the same pattern. The visible fight, GPU versus ASIC, training versus inference, NVIDIA versus hyperscaler, is downstream theater. Upstream of every visible fight is a small set of suppliers that quietly captures the margin. ASML for lithography, TSMC for fab capacity, the HBM Trio for memory, Broadcom for custom ASIC IP, and now Coherent and Lumentum for the optical fabric. The semiconductor industry rewards the company sitting one step upstream of the visible fight. Optics is the next step upstream, not because it is exciting on its own, fiber, mirrors, lasers, but because the bandwidth distance product is the constraint that decides whether AI scales further. In 10 years, when the AI compute story is told, the most valuable hardware decision will not have been NVIDIA's CUDA. It will have been Google's choice in 2018 to wire the pod with light. To recap, the chip war is not won by chips. It is won by light. Copper hit a wall. Optical broke it. Google's OCS proved the model. Co-packaged optics is the next leap. Two American companies, Coherent and Lumentum, sit at the bottom of every supply chain that ships optical hardware to AI data centers. The next video in the AI supply chain series steps back from the verdict pattern and asks the bigger question. We have spent 8 episodes naming the upstream winners: ASML, TSMC, HBM Trio, Broadcom, Coherent, Lumentum. What does this mean for how AI compute will scale through 2030? And what does it mean for the companies that have to keep buying from the supply chain? If you want the actual semiconductor industry view of the AI race, not the press release version, subscribe. See you in the AI Compute Economics video.